We will start the meeting in a few minutes.
Yeah, okay.
Good morning, everyone. Welcome to the day two of the faculty development program on new product development. In yesterday's session, we have seen the design of drone body, how we are using the Fusion 360 software to develop the CAD model. So in today's session, we will be seeing two parts. First thing is how you can do the finite element analysis using the Fusion 360 software, and then we will be using SimScale to perform the CFD analysis of the blade geometry. So the first thing that you need to do is to ensure the what are the parts which you want to do the analysis, whether they are present or not. So in yesterday we have split the drone body into two parts. One is the top part and another is the bottom part. So we want to perform the analysis on the bottom part because the weight of the electronics and weight of the drone and whatever the payload we are giving to the drone, that will be carried by the bottom part. So we need to convert this into a component before doing the analysis. So what we need to do is just right click on this body and you need to click on the create components from bodies. And so now the component is activated. This is the bottom part. And now you need to go to the simulation workspace. To enter into the simulation workspace, you need to click on the left hand side, which is the design, and you have the simulation workspace here. You need to click on that. And here in Fusion 360, you can perform so many types of analysis: the static stress analysis, modal frequency analysis, electronics cooling, thermal analysis, thermal stress, buckling, nonlinear static, and shape optimization, dynamic event, injection molding. So many modules are available. For today's session, we will be seeing the static stress analysis. You click on that and say create study. So once you click on the create study, you will be seeing this interface like this. It is taking some time to load. And so this is our drone body. Now we have entered the simulation workspace. Now what we need to do is we need to hide the components and ensure that only whatever the object we want, that is only present. And now we are going to perform the analysis on this. So the first part is to select the material. So as we are using ABS material for 3D printing the drone body, we need to select the material. So by default the material is steel. We need to change that. So there are various materials available within the Fusion 360. So I will be selecting ABS plastic. And I will click on OK. And if you want to check the properties of the material, you can see the properties here. So the ABS plastic is having a density of 1 kg per meter cube. Sorry, that is about 1 gram per cc. And then we have a Young's modulus of 2.24 gigapascals. The Poisson ratio is 0.38 and the yield strength is 20 megapascals. So whatever the stress we are obtaining in the simulation, it should obviously be less than 20 megapascals. Otherwise, we need to check the thickness of the material and try to increase the thickness. So now we need to assign the structural constraints. So the drone body is having a weight in the center and which is being lifted by the 4 different motors. So I will fix the bottom face of the motor casing. So these 4 faces I am selecting and I am going to fix them in all the 3 directions, UX, UI and UZ. And then I am going to click on OK. And now we have assigned the structural constraints. So this is the workflow. First we have assigned the material and then we have assigned the constraint and now we need to apply the load. And we are applying a structural load, which is the first option. And I am going to select this particular face. And you can see here whatever the force is obtained. So the total weight of the drone is going to be 1 kilogram and another 1 kilogram of payload will be there. So that is our assumption. So 2 kgs of load will translate to 20 newtons of force. So I am giving 20 newtons of force here. That is nothing but 2 kgs into 9.81. You will get around 19 newtons. I am rounding that to 20 newtons. And the force is obviously acting downwards in the direction of gravity. So I am going to click on OK. And I am going to select the management settings. general and mesh size. So mesh size you can alter here. So I'm going to leave it as a default option. I'm not going to change any of these settings. And I'm going to click on solve. It's not getting enabled. Let me check once. It's taking some time. So if you click the pre-check, so it is saying that visibility is turned off. So there is some error. In order to fix the error, we will export the design as a new file. I will export this as a new F3D file. Drone bottom. And I will open that particular file. And once we will check the materials, again I will assign the material here. And constraints. All these four faces will be fixed. And then loads. A force of 20 newtons. And now you can see that the pre-check is ready. And I'm going to say solve. So if you are using an education license, so the number of cloud credits it is going to consume is only 0, and you will be having unlimited number of cloud credits. And once you are set up the simulation, you can simply click on the solve the study. And this simulation is going to solve in the cloud. and it is going to give us the results. So it is not going to take much time. So the setting up is complete. You will be seeing the live update of the status of the simulation here. So our objective is to find the stresses and strains and what is the displacement value and whether it is less than the material strength or not. So we will keep a factor of safety of 2. So if the yield strength is 20 megapascals and if we are using a factor of safety of 2, so that will give us a limit of 10 megapascals. So we should ensure that stress is less than 10. So solving is complete. You can see the status here. And now you can see the results by clicking on the results tab. So it is going to take some time to load the results from the cloud. And you can see the results. So the first thing is to expand the load case. And what I will do is I will simply select in the results tab, go to the results menu. And now we are interested in finding out the stress. Click on the stress. And inside the stress, we want to see the von Mises stress. So you can see the von Mises stresses plot in this manner. So you can see that the maximum stress is only 6.65 megapascals. So this design seems to be a better design. And we want to see the displacement. To see the displacement, we need to enable the displacement here and total displacement. And you can see the total displacement is only 3 millimeters. That is 2.9 or nothing but the 3 millimeters. So you can enable the undeformed shape and a deformed shape. In the deformation tab, undeformed is undeformed, and then actual deformation. So this is only 3 millimeters of deformation, which is a very good thing. And so if you want to verify the results, you need to do the same thing in ANSYS. So I will show you the ANSYS workbench workflow. And till now, if you have any questions, you can ask. Any questions, sir? Hello? Any questions, sir? Isn't a circular base at the center better for aerodynamics than a square? Yes, sir. We can do that. So this is a demo purpose. Like the drone is only flying in the vertical direction, sir. So the shape doesn't matter much here, but we can do the CFD analysis as you suggested. So a circular will be a better thing than the square body. So I'm just showing a demo of how you can do the structural analysis. So now I will do the same thing in ANSYS workbench so that we can verify the stresses. So if you want to do the ANSYS, you need to convert the design file into a step file format. So I'm going to save this design in step format. So here you can select the step extension, and I'm going to name the file as drone bottom, and I'm going to select downloads as my location, and I'm going to click on export, and we will be noting and seeing whether the same results are being obtained in ANSYS workbench or not. That is the displacement of 3 millimeters and a stress of 7 megapascals. So that is our intention. So I'm going to enable the static structural, and the first thing is to check the engineering data. So the ABS material is somewhere similar to polyethylene material. So I'm enabling the polyethylene. And I will copy this material. And Young's modulus of ABS, let me check it. So it is around 1.1 gigapascals. So that is correct. And Poisson's ratio will be somewhere around 0.38. So I will edit the value here. And the yield strength will be around 20 megapascals. So I have edited my material. And the next thing is to import our geometry. I am going to open the file which we downloaded earlier, that is drone bottom in step format. So this is the geometry. So the first thing we need to do is assign the material. So I will then assign polyethylene 2. Polyethylene 2 is nothing but the properties which we changed for ABS plastic. And I am going to select a mesh size. So I have given a mesh size of 0.5 millimeter. And I am going to generate the mesh. So the body thickness is 2 millimeters. And I want to ensure that at least 4 elements are there across the width of the thickness. So I have given 0.5 millimeters as my mesh sizing. So while this is getting meshed, I want to perform the CFD analysis on the drone blade. So we will download a model of drone blade or the propeller blade. So I am entering drone propeller, and let's see if there are any ready-made models available in this website. So this is one of the models readily available. So I will download this model and import into Fusion. And for performing CFD analysis, we need to create the fluid domain around the object that we will do in Fusion 360. And we will be using SimScale CFD to perform the aerodynamic analysis. And our objective is that if the propeller is rotating at 1000 revolutions per minute, whether the drone will be able to fly in the air or not, whether the lift force generated on the propeller blade is sufficient to carry the weight of the drone. So that will be our objective. So I am just renaming the file. And I will open this file. So we can upload the SolidWorks file into Fusion 360 and then we can open it. So the advantage of Fusion 360 is that even though the design is not from Fusion 360, you can open Siemens NX file, you can open Creo file, you can open SolidWorks file, you can open CATIA file also. You may not be able to edit the design, but can definitely import and create the fluid domain around it. So for some reason I'm not able to mesh the geometry. So what I will do is I have reduced the size from 0.5 millimeters to 1 millimeter. And let's check if we are able to generate the mesh or not. So meshing is extremely processor intensive and RAM intensive. So sometimes your system might not support the higher resolutions. So that is the reason why we are using Fusion 360 Cloud. So Fusion 360 will not run the simulation in our laptop. It will run the simulations in the cloud computing in the Autodesk servers, and they will be having all the high-end systems there. And once the result is ready, you can download that and see in the Fusion 360. So I'm opening the propeller geometry and I will create the fluid domain around it. So this is the propeller. So we need to check whether the geometry is in the airfoil shape or not. As you can see, the cross section of the drone propeller is in airfoil shape. And so we can use this geometry for performing our CFD analysis. So what I will do is I will create a fluid domain around it. So I am going to select the sketch and select this plane. And I will draw a rectangle. and I'm going to give the dimension. This is 1000 millimeters, and I will make this also as 1000 millimeters. So before that, we need to check the size of the propeller. I will import it into the geometry and see the size. So the size of the propeller is very huge compared to our drone body. So we will reduce the size by 50%. So what you can do is you can scale the body, and I'm going to size it down. I'm going to enter 0.5. And I'm going to say update the child component here. Then automatically the size will be reduced. Now you can see that the size of the propeller is relatively better compared to previous one. So I will edit the sketch. And I will make it 500 mm. And this also I will make 500 mm. So the upstream has to be 250 mm. And I am going to say two sides. And I am going to say new body. And the downstream has to be 500 mm, which is the length of the blade. And then I am going to subtract this body from the drone body. I am going to say combine. I will select this body and I will say cut, and I will select the propeller body from this. And if you want to see the interior of the body, you can assign a clear material. And I will assign a clear water just to see the internal structure of the design. And you can see from here that we have subtracted the drone profile body from the fluid domain, and to perform the CFD analysis we will be making the air to enter this domain from this face and exit the domain from the other face, and so we will be able to see the fluid contour lines. And I am going to export this into step format. And now we have prepared our geometry using Fusion 360. Now we will be importing this into SimScale CFD. And I think our the structural analysis is been completed, and the mesh is ready. So we will finish this task and then we will go for CFD. I'm going to fix the supports. These four faces I will select. And I'm going to insert a force. And it is going to be 20 newtons of force. And in the solutions, I will insert von Mises stress as well as total displacement. And I'm going to click on solve. And while this is solving, we will log in into our SimScale account. I will share this link on your email as well. So SimScale is a free cloud-based CFD performing software. So you can use the application in your browser itself. You don't need to download the software. And this software is free for students and faculty members. You can simply mail to this company requesting for a free license, and you can share your like if you send the email from your education account, then they will enable the license for us. So I have my account already created, so I will log in with my account. and I will create a new project. And I will name this as propeller CFD. And you need to import the geometry from your computer. So we will be uploading the fluid domain which we downloaded from Fusion 360. And I will click on import. And then click on create simulation. And the simulation type has to be incompressible because of the velocity is very less. It is less than 0.3 Mach number. So the flow is going to be incompressible. But depending on your case, you can select the various other options. And this is the fluid domain which we created. And you can see that the internally the blade geometry is created like this. So I will first assign the material. The material is going to be air. And then we need to assign the boundary conditions. So we have to do some calculation. Let me open that for you. So the motor is rotating at 1000 RPM. And our geometry is having a length of around 250 mm. Let me measure the distance from this point to this point. So this distance is 138 millimeters. So 138 millimeters, and we are measuring the velocity at the center of the propeller. So 138 divided by 2. So that is 69 millimeters. And the linear velocity v is going to be it is going to be pi d n by 60. The n is 1000 RPM. So this is nothing but r into omega. So r into omega we have converted in this manner. So I am calculating in my phone. This is 3.1416 into 0.138 into 1000 rpm divided by 60. So that is giving me a linear velocity of 7.2 meters per second. So this one you will be converting millimeters into meters. So that is what we will be entering here as inlet velocity. This is the inlet velocity and it will be in the negative x direction. This is 7.2 meters per second. It will be inverse. So our air is entering the fluid domain in this manner, and the other boundary condition is going to be pressure outlet. So this space is going to be acting as a pressure outlet with a gauge pressure of 0. So it's the standard practice to give 0 gauge pressure outlet at the outlet of the fluid domain. And this particular valve we will be selecting as a symmetry valve. And what I will do is I will hide these spaces and then give a named selection to the all faces of the propeller. I will select all these faces and I am going to save this as propeller body. And now I am going to mesh the body. So these are the various settings to mesh the fluid domain. I am going to enter a fineness of 6. And I am going to click on generate. So it is going to mesh our domain for us. And while the meshing is going on in the cloud, you will see the ANSYS results. So there is some error coming up. So what I wanted to say is, what is the approach which you will be using for analyzing the geometry using ANSYS, and I will resolve the errors, and then I will let you know the results in the next class. So what we are trying to do is we want to verify the Fusion 360 results with the ANSYS, and both the results will be same so that we can validate our model. So it is saying that there are some self-intersecting faces. Let's verify this and try to resolve the error. So the error is coming somewhere at this location. It is saying that the faces are getting intersected. Let's try to rectify it. Or what we can do is we can design our own propeller. So I will quickly create, using the splines, I will create a propeller geometry. I'm using the spline to create the aerofoil shape. And I'm going to use the loft command. I'll select this profile and then this profile and then this profile. And the propeller blade geometry is ready. And if you want to generate specific aerofoil shape, you can use the aerofoil generator tool. I will show you that also. So the airfoil shapes are generated by the NACA digit profiles. NACA stands for National Advisory Committee for Aeronautics. So you can download this data and upload into Fusion 360. So if you want to generate an aerofoil profile here, you can simply go to aerofoil and select the NACA profile like this, and how many points you want and what is the profile. And if you click OK, the NACA aerofoil profile will be generated like this. You can see how the profile is generated directly using the Fusion 360 extension. And now what I will do is I will create the fluid domain around this. So the upfront length has to be 200 mm. And the downstream length is 500 mm. And the height is 250. And now I am going to extrude this profile. And I am going to say this as a new body. and I'm going to subtract this propeller body from the fluid domain. And I will export in step format. So export is complete. So I will go back to the SimScale interface, and in the geometry I'm going to say delete the geometry and create a new one. And I'm going to assign the material of air. And now I will assign the boundary conditions. Velocity inlet. This is going to be in the y direction. You need to be careful in which direction the air is entering. So air is entering in the positive y direction. So here you will enter a value of 7.2 meters per second. And then you will give a pressure outlet. This is going to be the pressure outlet. And the center wall is going to be a symmetry wall. This wall will be a symmetry wall. I am going to hide this face and give a named selection. I am renaming these files, these faces, and I am going to save this as propeller body wall. And in the results control, I want to find out the lift and drag plot. For that, I will say forces and moments. I am going to select the propeller body wall as my faces. And this is going to be lift force. And similarly, I will create another one for the drag force. and I will say forces and coefficients. The lift direction will be in the positive z direction. The drag direction will be in the positive y direction. So this will be 1 and this will be 0. You need to check in which direction the drag force is acting and in which direction the lift force is acting. And the free stream velocity is 7.2 meters per second. And reference length is 22 millimeters. And we need to enter value of reference area. In order to find the reference area, we'll go back to Fusion 360. And I'm going to create a sketch on the XY plane and check its area. So this is the projected area of the aerofoil. And it is going to give me an area of 2617 millimeter square. You can see the value in the bottom right corner. If you select the particular sketch, you can see the value as 2617 mm square. And I want to convert mm square into meter square, or you can also select mm square in the mm square option is not there. So this is 2617. So that is 0.002617. So I'm going to enter the reference area value as 0.002617 here. And the assigned faces are going to be the named selection, which is the propeller body wall. I have selected it. And now we can run the simulation. So while this is running, I want to show you some of the simulations which we done previously. So this is the CFD analysis of a sphere. And this is the CFD analysis of an aircraft body. So I am not able to load them. I think there is some licensing issue. So we'll wait for some time. This simulation is almost about to complete of the propeller blade, and I want to show you the lift and drag force. So the mesh is generated successfully. You can see the mesh. So this is the CFD mesh. You can see the inflation layers as well. So ideally, it is better if you use the ICEM CFD measure in ANSYS and then import that into SimScale. That is also possible. But if you want to see the results quickly to get an idea, you can use the default measure available in SimScale. So it took only 2 minutes to mesh this. So the advantage of SimScale is that you can simply sign out of the application and then you can sign in after some time. So this is the previous project which I have carried out. Let's see if we are able to see the results or not. So this is the front wing of a Formula racing car. So we can see the pressure plots as well as the velocity plots. So you can see that there is low pressure below the wing surface and there is high pressure above the wing surface, which is going to create the downforce. And you can also see the force and moment coefficients. So this is the lift coefficient. It is showing a negative value, meaning that the force is acting downwards. And you can see the drag also. The drag coefficient is roughly around 0.11. So that is the drag force acting on the surface. So we have completed the simulation up to 30%. So after that you will be able to see the results here. The simulation runs. So I will summarize what we have seen so far. We have seen the introduction to product design and we have developed the design of a drone body yesterday. And we have seen how to export the geometry as step format for performing the analysis. And we have seen how we can convert the geometry in STL format for 3D printing. And we have seen how you can insert the MechMaster CAD standard components like screws or any other standard fasteners without designing them. We can directly import them into Fusion 360. And we have also seen the GrabCAD library wherein we can download readily available models for our analysis or any other purpose. And today we have seen the structural analysis of drone frame in Fusion 360. And we wanted to verify that in ANSYS structural, but due to some error we couldn't do that. And then we will see the slicing using the slicer for 3D printing. That one we will see now. And injection molding we will discuss tomorrow. I mean not tomorrow, that is the next classes on upcoming Saturday. And what are the 3D printing partners and how we can get an online quotation, that one we will see. And finally we will see if you are interested to start up a manufacturing company, what is the registration process. That will be the final go to market stage. So I will open Slicer. So Creality Print is a slicing software which will be used for 3D printing. So depending on the manufacturer of the 3D printer, they will supply their own slicing software which will convert our STL file into G-code format. That file we will copy in our SD card and load it onto the 3D printer. So this is the Creality slicing software. I will open the file. Yesterday we downloaded the drone body object in STL format. So I want to scale this down. Now you can see the STL file is being laid down. Now you can slice this. These are the various settings, like what is the layer height, what is the default line width you want, those settings. So we can go with the default settings. And if you click on slice the plate, the STL file will be converted into G-code format. And you can see all the individual layers. And now you can click on export G-code. And it is going to show me a time of 1 hour 8 minutes. So within 1 hour, you will be able to 3D print this. If you have a 3D printer, if you don't have a 3D printer, you can give that file to any 3D printing company and they will be able to manufacture the part for you. So we are trying to optimize our 3D printing geometry. What will be the material used? How much material will be used? Those things. It is showing it as filament will take around 14 grams and filament length of 4.7 meters. So all this data will be shown here. Exclusively on slicing the 3D printing file and giving for 3D printing, I have created a separate playlist on my YouTube channel. I will share the link with you. And in the meantime, if you have any questions, you can ask. The simulation is around 78%. I hope it will be done very soon so that you will be able to see the results. Any questions, sir?
Sir,
Yes, sir.
sir, I want to tell you that this analysis which you have done here It is available on YouTube or by you or not?
The answers part, sir, you are asking?
Yes, yes.
That is not available on YouTube, but I am recording this today's meeting, sir, which I will upload on YouTube. And if you want detailed videos on ANSYS, then I will make the videos and I will send you, sir, after the workshop.
Okay. Okay, I want that.
Sure, sir.
Okay, sir.
Like mainly, I would recommend using Fusion 360 because it is very fast. It will not give any modeling errors. But if you want dedicated videos on ANSYS, that I can make and I will share that, sir.
Okay, sir.
So the simulation shows 96%. We are almost done with it. So the simulation is completed. So now you can click on post process the results and we will be able to see the velocity and pressure plots. And here you can see the pressure contour. So you can see that there is negative pressure on top of the aerofoil and positive pressure at the bottom of the aerofoil, which is indicating us that there is a lift force generated on the propeller blade, and we can see the value of the force by expanding this force coefficients. So the lift coefficient is roughly around 1.2, and let's see the total force. So our lift force is in the direction of Z direction. So we are getting a total force of around 0.1 newtons. So lift coefficient is coming around 1.2. Let's try to calculate the total lift force. It is half times CL times area of the blade times density of the air times velocity square. So we will substitute the values. We are getting lift force, that is CL of 1.2. So this is giving me a value of 0.1 newtons. So if you divide it with 9.81, it is giving me a value of 0.01 kgs. So this is the lift force. This is not sufficient enough to lift the drone. So we need to increase the velocity. So that is how we can perform the analysis. If this velocity is around, let's say 5000 rpm or something like that, then the velocity will change. So we need not do the CFD analysis again and again, because we know the value of the lift coefficient. In this variable, only the velocity will change. So if it is 5000 rpm, the velocity is coming around 36. So it is 36 meters per second. If you substitute this back, so that is giving me a value of 2.5 newtons. So that is giving me a value of 0.25 kgs. So if you are using two blade propeller, on each blade it will give you a value of 0.5 kgs, and total 4 propellers we are using. So that will be total lift is equal to 4 into 2 into 0.25. That will give you a value of 2 kg. So we are able to balance the drone up to a total weight of 2 kgs. So like this we can design our propeller, and we can design our drone accordingly. So we need to select any motor which will rotate at a speed of 5000 rpm. So the objective of the CFD analysis is to find out the lift coefficient using the sim scale, and we were able to successfully do it. And this is what I wanted to show in today's session.
Sir, that lift force, where you have got the coefficient of lift.
Yes, sir.
So the coefficient of lift from where you have get.
Yes, sir. So from the sim scale, sir, here we created one lift coefficients and force coefficient, no, sir. In this plot, so the software will give the moment coefficient as well as drag coefficient, lift coefficient, sir. If we deselect them and select only the lift coefficient, so from here, sir, you can see 1.2, 1.3 like that.
Okay, okay.
So it will converge after 1000 iterations, sir. So roughly after 100 iterations, it is converging around 1.2, 1.28 like that. So I rounded off to 1.2 only. Is it clear, sir?
Yes, sir.
Okay, sir. So injection mold development, this one we could not cover in today's class, but this one we can do in Fusion 360, sir. Once we have 3D printed our model drone body, if we want to go for mass production, how we can develop the injection mold for it. So Fusion 360 is having mold flow analysis built in into it, sir. That module we will discuss in next class. In the coming Saturday, we will discuss that in more detail. And in the WhatsApp group, please mention any doubts you have, sir, so that we can cover it in the upcoming class, sir. So I think that's it for today. I wanted to share.
Sir, the WhatsApp group, I have not joined it.
I think um, I will share the WhatsApp group link, sir. You can join that.
Okay.
Fine, then. Thank you so much for today's attendance, and you will get your certificate after the last on your fourth day. In the next Sunday, by next Sunday evening, you will get your certificate.
Okay, sir.
Yeah, thank you for joining. I'm concluding the meeting now. You can leave the meeting. Thank you for the day. Have a nice day.
Thank you.